1 second. Okay, can you see my slide? Okay.
Yes, everything is fine.
All right.
The live streaming on YouTube has already started, I see. Okay, and I think we can start. So welcome everybody in the afternoon session. The afternoon session is online, but here in the auditorium we have a large audience also. And our first speaker for this session is Eran Palti, who will tell us about convexity of charged operators and CFTs and the weak gravity conjecture. So Eran, we are all ears.
Oh, okay. Well, so let me begin by thanking the organizers for the opportunity to speak. It's a pleasure, although it would be a greater pleasure to be there in person, but okay. The title of my talk is Convexity of Charged Operators in CFTs and the weak gravity conjecture. And this is work that came out a few weeks ago, maybe a month ago now almost, with Ofer Aharoni. Yeah. Let me just, okay. So an old idea is that in quantum gravity, there are no U1 global symmetries. Let me just move the screen away. Okay. And the simplest argument for this is that if you take a theory, gravitational theory with a U1 global symmetry, then you can make a black hole in that theory. And because of the no-hair theorem, the black hole will not reflect any of its global symmetry charge on its horizon. So you cannot, and therefore, whatever charge it has, it looks the same. That means there's an infinite number of microstates associated to a black hole of a given mass. So it could have a microstate of any given global symmetry charge. And this is in contradiction with the expected finite entropy of an expected Bekenstein-Hawking formula for finite entropy for finite mass black hole. So I think this is perhaps the simplest argument why quantum gravity should not have a U1 global symmetry. Sorry. It's possible to rephrase this argument. It's not an exact rephrasing, but it's almost an exact rephrasing in terms of an infinite number of stable black hole remnants if you have a U1 global symmetry. So the story is you just take n copies of a particle charged under this U1 global symmetry, you throw them into a black hole. That gives the black hole a charge n, and then you let the black hole evaporate all the mass of the particles you just threw in. In fact, you can just let it evaporate all the way down to the end of the semi-classical regime, so near the Planck scale. And then you get some object which has some charge n, since it cannot emit any charge, but a very small mass, so a Planck scale mass. And this object is called a remnant, and it's completely stable because obviously it cannot decay back to the particles that you threw in the first place because it doesn't have enough mass to do so. And now you can repeat the same game with one more particle or any number of particles you like to start off with. You always get some stable Planck-sized remnant of any charge. So that's an infinite number of remnants, and these are essentially almost exactly analogous to the infinite number of microstates of a given black hole that led to this contradiction with the entropy. And we can rephrase things again in a slightly different way. This is not really an exact just rephrasing, but it's very closely related. So instead of forming the remnants by starting from a huge black hole with a large number of, you throw in a large number of particles, then letting it decay down, you can kind of build them up from the bottom up. So you just imagine you have the gravitational theory with U1 global symmetry, and you take some particle charge under this global symmetry, and you take it and its copy next to each other. Then the two of them will attract each other, and they will form a gravitational bound state because you have gravity in theory. And what is easy to see is that the mass to charge ratio of the bound state I don't know if you can see my arrow, the mass to charge ratio of the bound state is going to be less than the mass to charge ratio of the particle, because the charge of the bound state is going to be twice the charge of the particle, but the mass is going to be a little bit less than twice the mass of the particle, because there is a binding energy. And it's easy to show that any object can only decay to a different object if the object that it decays to has a smaller mass to charge ratio than itself. And since the bound state has a smaller mass to charge ratio than the particle, it cannot decay to the particle, and therefore it's a completely stable bound state. If you have multiple particles in your theory, then you just have to form it using the particle with the smallest mass to charge ratio in the theory. So again, it cannot decay to anything else. And now you can play the same game by adding another particle and so on. So you have 3, 4, 5 particles, and as many as you want. And this way you're forming these completely stable states that cannot decay because of the charge that they carry. Eventually you'll form a black hole, and then you make a connection to the story we just discussed. But this is a kind of nicer way to think about it a little bit, as we'll see. Yeah. Okay, so now what happens if we have a gauge U1 instead of a global U1? Then if you gauge the U1, it kind of modifies the story, because now if you put a particle next to itself, it will not just feel a gravitational attractive force, but also will feel a repulsive force due to the gauge U1. And there's a completely analogous condition, which is, as we said, all these things are connected. If you have the black hole and you have it charged under a gauge U1 symmetry, then it's no longer true that it will emit Hawking radiation down to the Planck scale or to some fixed mass, because it has the extremality bound, so its mass cannot go below its charge in Planck units. So gauging the U1 modifies the story, but we see that if we send the gauge coupling of the U1 to 0, then we just recover the same physics we had before. So everything just goes back to the way it was before, and which was this kind of inconsistent situation. So the idea is that, well, it's not enough to gauge the U1, but you have to gauge it strongly enough. Okay, you can't just gauge it arbitrarily weakly. So strongly enough with respect to what? Well, there's only one other player in this game, that's gravity. So it should be strong enough with respect to gravity. And we can make this more precise just by looking at the picture. What do we mean by strong with respect to gravity? Well, the natural statement is that it should be so strong that the repulsive force between the two particles beats the attractive one, and then we just don't have these completely stable bound states anymore. In terms of the black hole, that's precisely the same as saying that the black hole, the particle is such that an extremal black hole can decay to it, and that way it can discharge itself, and you avoid these stable states. So that's the weak gravity conjecture. That the weak gravity conjecture proposes that we should not just gauge a U1 arbitrarily weakly, but we have to gauge it stronger than gravity in that sense. So that avoids having any stable bound states or stable black holes. It's not clear this should be true. That's why it's a conjecture, but this is the logic. I think it's one argument in terms of logic that you can follow to reach it. Of course, so what this means is that you have to have a charged particle in the theory with a mass smaller than its charge. And these kind of arguments are backed by evidence from string theory, at least where all the known tests in string theory seem to pass. So that's good evidence. So now you can just take this logic and you can just push it into more and more interesting, if you like, or complicated setups. So for example, let's say we add some massless scalar fields to our theory. Then a massless scalar field also mediates a force, a self force between the particle and its copy. Now it's an attractive force. So now the natural statement is therefore that the repulsive force should beat the attractive one, so you don't form these stable bound states. So we should reformulate the weak gravity conjecture, if you like, as the statement that the repulsive force should beat the gravitational attractive force plus the scalar field attractive force, the force mediated by the scalar fields. And one can test this reformulation. And again, in string theory, it seems to pass known tests. And so that's one generalization we can consider. And the generalization that we're going to be considering in this talk and in the paper is what happens if you're in anti-de Sitter space. Let's follow the same logic again. Now, if we're in anti-de Sitter space, then anti-de Sitter space essentially acts like a box. And that means that when you have this particle and its copy, you cannot separate them arbitrarily far away from each other. What this means is that when we think about forming these bound states, we should not just consider the long-range Coulomb forces. So in flat space, we can just take the particles infinitely far away from each other, and then the only forces acting on them are the long-range Coulomb forces. And to say that there's no bound state, it just means that the repulsive gauge force beats the attractive in the scalar force. And that's the way that the gravity conjecture was formulated then. But if we're in ADS space, we can no longer do that. And so we have a finite separation, and that means we should reformulate it a bit more precisely. And the more natural or accurate formulation that we propose in anti-de Sitter space is what we call the positive binding conjecture. And that's just directly demanding that there should be a positive binding energy between the particle and its copy, so it doesn't form this bound state. So the statement is that for a weakly coupled gravitational theory with a U1 gauge field, there should exist at least one charged particle in the theory with charge of order 1. So this is a condition that we can consider, which has a non-negative self-binding energy. So one example we can consider is 5-dimensional anti-de Sitter space, just to see what it means. What is the difference between the non-negative binding energy and the long-range forces that we discussed? So we consider anti-de Sitter space, I mentioned anti-de Sitter space, and we have this particle phi, and it's charged under some gauge field. And we have the mass term, the gauge field kinetic term, but now we add contact terms to this theory, so phi to the 4 kind of terms. And if we were in flat space, we could take the particle infinitely far from its copy, and then all the contact terms would just disappear, and the only thing we would care about are the long-range Coulomb forces. But because we cannot do that, there is a known trivial wave function overlap of the particle and its copy, and therefore contact terms contribute to the binding energy. So one can do the precise calculation, it was done in this nice paper, and you find that the binding energy receives 3 types of contribution, one from photon exchange, one from graviton exchange, and one from these quartic contact terms. And they are comparable in magnitude in general. This is the expressions for them. And I just introduced this delta, which is just related to the mass of the particle. We'll see what it means more precisely in a second. And these are the expressions you find. And so now we see, what do we mean precisely by the positive binding conjecture? We mean that the total binding energy, which is the sum of these 3 contributions, should be positive. And that's clearly different to just saying that the statement of the photon and graviton exchange should be positive. Of course, you can also add massless scalar fields to this story. This will just give you another contribution and so on. I don't know if people ask questions, or you can ask questions, but yeah, I'll just keep going for now. You can ask questions also at the end of the talk. Let me continue. Okay, so the nice thing about anti-de Sitter space is that, well, if you have some statement about a gravitational theory, then you would expect some statement for the conformal field theory dual. And the nice thing about the formulation... yes, there's a question.
Can you hear me?
Yes, I can hear you.
There is a question.
Okay, good. Yes.
Hi.
Yes, no.
Oh. Can you hear me, Eran?
Yes, yes, Dieter.
Maybe this question comes too early, but do these formulas have a natural flat space limit? So in case you take the ADS radius to infinity, do you get what we had before in Minkowski space?
Right. So, sorry, I can hear my echo. Maybe to, yeah. So the formulas have a. Thank you. The formulas have an actual flat space limit, of course, and perhaps the simplest way to see the flat space limit is to take the mass of the particle very large relative to the radius of anti-de Sitter space. The radius of anti-de Sitter space doesn't appear in these formula because we set it to 1. So that's the natural statement. So in some sense, taking the radius of anti-de Sitter space very big is like taking the mass of the particle big, which means the wave function gets localized. So the quartic interactions are coming because of wave function overlaps between the particle and its copy. But if you localize the wave function, then there's no overlap. And that's similar to taking the particle and infinite part of each other away from each other. And so indeed, you can show that the photon and graviton contributions dominate over the quartic contribution if delta is big. Of course, it depends on what A and B is, but if you look at supersymmetric theories, for example, then indeed this contribution drops out in that limit. I hope this answers at least partially the question. Or
there is a follow-up.
Yeah, in one of our common papers, we have seen that the flat space limit of ADS gravity is very problematic. So you will get swamped by other scalar fields.
Of course. So this calculation is done in an effective theory. This is a calculation done in effective theory, which doesn't include, of course, some UV modes that might appear if you take that flat space limit. So the effective theory that is used to do this calculation could break down in a flat space limit. But that's why I think it's better to think of it not as a flat space limit, but as the limit where the wave function of the particle is very localized relative to the ADS scale. So in terms of the binding energy of particles and so on, I think that's the natural limit that you expect to recover. But it's true that if you did this in a complete theory of quantum gravity, in the flat space limit, you would likely have tau mass states, and it's not even, we don't even have well understood examples where it even makes sense to think about the pure ADS, because the ADS curvature is usually the same size as the internal curvature. But this is a calculation in some supergravity effective theory. Is that okay? Or
yeah, please move on.
Yeah. Of course, whether such an effective theory can be realized in string theory is a different statement, but the binding energy is a well-defined quantity irrespective of the effective theory that you use, of course. Indeed, we will see that you can define it even if you don't even have a Einstein gravity, or even if you don't have a local theory, it's still a well-defined quantity.
May I ask a question, Eran?
Yes.
If the wave function of the particle is very localized, so everything is localized in the subregion, how does the global structure of space-time enters?
It does not. So that's why I'm saying that if you take the mass very large, so the particle becomes localized, then the quartic interaction to the binding energy goes to 0 relative to the photon and graviton interactions.
Okay. And then there is a difference between being in anti-DS or anti-de Sitter or being in Minkowski?
Well, eventually it goes to 0. I mean, if you take a delta function, of course, then you don't feel the global structure.
Okay.
But there are finite corrections, of course.
Okay.
Yeah. Okay. So the nice thing is we have a CFT dual to the binding energy, which is very neat and sharp. It's basically the anomalous dimension of the operator phi squared. So here the anomalous dimension doesn't mean the dimension of the operator take away its classical dimension. It precisely means what I write here is the dimension of the operator dual to phi squared minus twice the dimension. So call phi the operator dual to the field phi. Then it's the dimension of phi squared minus twice the dimension of phi. That's exactly what the binding energy means in the CFT dual. So you may ask, okay, what is the operator phi squared? Well, phi squared is the leading operator in the operator product expansion of phi times phi. Okay, so that's precisely what the CFT dual of the binding energy means. And now if we rewrite this not in terms specifically in terms of the operator phi, but in terms of the charge of the operator, then that means that if we give the phi charge q under the U1, okay, the gauge U1 in the bulk goes to a global U1 in the CFT. The field phi, which is charged under the U1, goes to an operator, which we call phi again, in the CFT, and that operator is charged under the global U1 symmetry. Let's call this charge Q. Then the statement is that the dimension of the lowest dimension operator of charge 2Q is minus twice the dimension of the lowest dimension operator of charge Q must be positive. Okay, so all we did here was rewrite the statement in terms of the charge of the operator rather than the operator itself. Okay, are there any questions about this? So that is what this formulation of the weak gravity conjecture means in the CFT dual. And now we can formulate this completely generally. We see that this formulation is just a statement about dimensions of operators and charges of operators. It makes no reference to forces or to a weakly curved gravitational dual, no reference to these things that we taught about, wave functions, quartic operators, and so on. it doesn't even need locality. It doesn't make reference to a locality in a gravitational dual. It's just a completely general and simple statement about the CFT. And so further, there are no sharp differences between CFTs that have a weakly curved gravitational dual and a strongly curved gravitational dual. If there is some statement that's an exact statement that holds for any theory with a weakly curved gravitational dual, but holds exactly so it's exactly an equality, one would expect it to hold once you include higher curvature corrections and possibly even when you go to some strongly curved gravitational dual. So motivated by this, we propose that in fact this property holds for any conformal field theory, whether it has a weakly curved gravitational dual or not. In some sense, every conformal field theory has a gravitational dual. You can do this also by definition, but that gravitational dual might not be weakly curved. It might be some strongly curved theory, might have some many higher spin fields and so on. But the binding agent formulation has no problem handling this because it makes no reference to gravity or to gauge fields at all. So this is the general formulation we propose. We call this the Abelian convex charge conjecture. So consider any CFT with a U1 global symmetry, denote by delta Q the dimension of the lowest dimension operator of charge Q, then this must satisfy a convex-like constraint. So the dimension of N1 of an operator of charge N1Q0 plus N2Q0 must be bigger than the dimension of N1Q0 plus the dimension of N2Q0. And this should be true for any positive integers N1 and 2 for some Q0 of order 1. So the statement that Q0 of order 1 is actually really the non-trivial part of this statement. It's really one of the, not the only, but it's the main non-trivial part of it, Q0 order 1. And this is really what's capturing the weak gravity conjecture. So if we think back to this logic of the bound states, then one can, so what is this convexity telling us? It's telling you that as you increase the charge, you increase the mass to charge ratio, okay? But if you could form bound states, then you would decrease the mass to charge ratio as you increase the charge. In other words, the operator which has the lowest dimension to charge ratio would be something of huge charge because you just form it from lots of bound states. The fact that you cannot do that means that the spectrum stays convex already from some Q0 of order 1. So this is why we're capturing the weak gravity conjecture by this. Are there questions about this? Sorry. Okay. So this is the general formulation. Yes? There was a question or not? Okay, I carry on. And before I talk about tests of it, you can also formulate it more generally. It's in terms of not just U1s, but any non-abelian symmetry is the following statement. Consider any CFT with a continuous global symmetry G. Consider a simple factor G0 and G. Donate by delta R the dimension of the lowest dimension operator in representation R of G. Then there is, so G0 is like the analog of the U1. Then there is always some representation R0. R0 is the analog of Q0, which is non-trivial in G0 and has weights of order 1. So weights of order 1, that's the analog of Q0 order 1. Such that the dimensions of the lowest dimension operator, which transforms as a symmetric product of the representation R0. So Q symmetric product of representation R0. So that's like the Q is like the N times Q0. I should have called Qn probably. Satisfy the convex-like constraint as we did before. So basically, instead of taking Q0, you take some representation R0 of the non-abelian symmetry with weights of order 1. And instead of taking N times Q0, you take the N symmetric product of that representation. Okay, so that's the conjecture, and now we can test it. And the most non-trivial and interesting tests are in CFTs, which don't have a weakly curved gravitational dual. So tests on the CFT side. And this is what we'll talk about. So before we talk about specific tests, let me talk about some general properties of CFTs. So if you take a sufficiently generic CFT and you take the charge sufficiently large, then you enter what's called the large charge regime. And that spectrum, then the spectrum is convex in the charge. So if Q is sufficiently large in a sufficiently generic CFT, you will have a convex spectrum and the conjecture will be satisfied. So if Q0 is sufficiently large, it will be satisfied. So of course, the non-trivial part is that Q0 should be of order 1. Now, if you have a completely strongly coupled sufficiently generic CFT, so you have no small parameters in it at all. So what does large Q mean? It means larger than any large parameter in the theory. But if you have no large parameters in the theory, then large Q just means Q order 1, and so the conjecture will be satisfied. So any sufficiently generic CFT, which is completely strongly coupled, will satisfy the convexity conjecture. So that's good. If you have a supersymmetric CFT, then you can look at BPS states, or if you have a free scalar theory, then the spectrum is linear in the charge, and then it's marginally convex. So those kind of theories will also satisfy it. You can also look at free fermionic theories, and in free fermionic theories, the spectrum is not even marginally convex if you take Q0 equal to the number components of the fermion, which is a more than one number. And that's because the Pauli's exclusion principle means that if you try to increase the charge by putting on more fermions into the operator, then because they're Grassmannian in nature, you cannot do that. You have to also include derivatives into the operator. And derivatives increase the dimension, but don't increase the charge. So you will inevitably make the spectrum more and more convex. So for example, in 3 dimensions, you have this spectrum, and you see that this is not even marginally convex. So the dimension of charge 2 plus the dimension of charge 3 is not even marginal with respect to the dimension of charge 5. Okay? So what that means is that if you take any fermionic theory, and you take any small perturbation of the free theory, so any kind of like large N control or small coupling, then the spectrum will stay convex because it's not even marginally convex. It's not convex by order 1. The only way to avoid it, the only non-trivial test you could possibly do of the conjecture with a fermionic theory is if you have a very large number of fermions. So then you don't have this, you don't have to insert derivatives if you're forming large charge operators. So if you have, let's say, fermionic theory with some SUN gauge theory and you send n to infinity. So that's the only situation where you can avoid it. But any theory with a small number of fermions will automatically satisfy the conjecture if it's perturbative. If it's non-perturbative, then you have the large charge argument, which we gave, which will also satisfy it. If you have some explicit theories, which we'll look at now, then you can also, weakly coupled theory, you can identify the operators with actual fields, and then you have this relation between the powers of the fields, and this needs to be positive. And so you can test this. The simplest theory you can test it is the Wilson-Fisher fixed point in U1 theory, and one can do this calculation, and you can show that it's indeed positive, and the spectrum is convex. In fact, it's convex even for large kind of couplings, so large epsilon, but I won't go into that because I'm running out of time. You can consider the ON model in 4 minus epsilon dimensions. And again, one can show that the spectrum is convex. You can consider the U1 and ON sextic model in 3 minus epsilon dimensions. All these things CFTs, and the spectrum is convex. You can consider now theories. So those are theories that were done in the epsilon expansion. So they are done essentially as a weak coupling expansion. Now you can consider theories in full number of dimensions, whole integer number of dimensions, and you can use large N to do the calculation of the dimension. So you can consider the ON quartic model in 3 dimensions, and that is indeed, one can show the spectrum is indeed convex. You can consider the ON model in 5 dimensions, the quartic model, or the ON cubic model in 6 minus epsilon dimensions. You can show those cases the spectrum is not convex. But those theories are also known to be non-unitary. Okay, so we're insisting on unitary CFTs. So that's quite interesting. So we have examples where the conjecture is not satisfied, the spectrum is not convex, but those theories are also not unitary. Another thing you can consider are gauge theories in weak coupling. So for example, you can consider like Banks-Sachs types fixed point CFTs. So you can, in this case, you can consider SUNC gauge theory with NF massless fermions, but NS massless scalar fields. And you consider the global symmetry rotating the scalar fields, and you consider operators charged under that. So these are mesons. Because you have scalar fields, you also have these other marginal operators, the quartic operators you have to put into the CFT, and you have to look at a fixed point for the whole thing. The things we want to look at are these meson operators, phi star phi. So not phi dagger phi, that's a singlet under the global symmetry. We want to give them 2 different flavor indices and raise that to the power of n. And one can calculate the anomalous dimension of these guys. Well, the difference between this 2 meson operator minus twice the 1 meson operator, that's the calculation we did in the paper. And one shows that it's proportional to some positive constants times this h tilde plus f tilde. And this h tilde and f tilde must themselves be positive in order to have a stable vacuum of the theory. Otherwise, you don't have a vacuum of the theory, you just have a runaway. So if the theory is to have a stable vacuum, these must be positive, and therefore the spectrum is convex. So we see a beautiful relation, a precise and exact relation between convexity and stability of the vacuum. One can also consider strongly coupled gauge theories where you do the calculation by going to a large number of flavors. For example, 3-dimensional UN gauge theory with NF fermions flows to a CFT in EIR. It has a U1 topological global symmetry, and the operators charged under it are monopole operators. And one can compute these using semi-classical methods. So this is the case for pure theory with NF fermions. And you see that the spectrum at large NF is convex. So these are the dimensions. So, you know, if you take 2 times Q1, you get less than Q2. And so the spectrum is convex. One can do a similar computation if you have scalars instead of fermions. And you can have with or without quartic terms. If you have quartic terms, it's called the CPN model. If you don't have quartic terms, it's called the tricritical model. And you can see this is the leading contribution to the spectrum. And you see this spectrum is, again, convex. The numbers are convex. So if you take 1 plus 2, it's less than 3, and so on. One can also consider fermion theories with quartic couplings. Okay, so now we're doing a large number of fermions, and we introduce quartic couplings. So this is the picture here. One finds, again, the spectrum is convex. You can also add Chern-Simons terms to this theory at level K. These are whole new classes of theories, but you find that the spectrum becomes monotonically more convex with increasing K. So Chern-Simons terms just make the spectrum more and more convex. So it passes also all that test as well. And finally, let me mention an interesting example where we can think about strong versions of the conjecture. So for example, you can consider the following statement that Q0 is the state of lightest charged operator, for example, or Q0 is the charge of the smallest scalar operator. And to test those, we can test those in completely strongly coupled theories, okay? Because if we had completely strongly coupled theory, then we said that the weak version of conjecture will be satisfied, because if you take Q0 large enough, you will enter the large charge regime, and large enough just order 1. But if you want it to be fully convex, the spectrum, so starting from the lowest, smallest Q0, then there is a non-trivial test even in fully strongly coupled theory. So for example, you can look at the O2 model in 3 dimensions, and you can calculate the dimensions using these different methods, and you see that the spectrum is convex, fully convex. So in fact, in all the examples we looked at, these strong versions were even satisfied. And just one last comment. Okay, good. So just one last comment. This theory is very interesting, the O2 model in 3 dimensions, because it's a theory that's expected to describe the superfluid transition in helium, the so-called lambda point. And that means that, in fact, these calculations of the dimensions of the CFT operators actually can be experimentally measured. At least one of them has been experimentally measured. So that's the one for the global symmetry neutral operator. So you see this table. Oh, sorry. There is this is the calculation of this the dimension of this operator, and this is the experimental measurement. For the charge operators, there is no experimental measurement, but in principle, it can also be done. And so I think this is a very tantalizing possibility that if the conjecture is really correct, and if the strong versions of it are correct, then it's true for any CFT. Then even if we don't know the CFT, and if we calculate the dimension of charge operators, in principle, we could experimentally measure them. And in that sense, it could even give you experimentally measurable predictions. So to summarize, we propose that the natural formulation of the weak gravity conjectures in terms of the self-binding energy of the particle. This leads to a CFT dual statement, which is that the spectrum of charged operators should be convex in any CFT. It seems to hold in all the examples we tested so far, but we don't have a general argument or proof for it from the CFT side. So it's very important to keep testing it or try to prove it or disprove it, finding counterexamples. And if we found them, then try and understand what is special about them. And as I said, there is this, in principle, since any phase transition is described by some CFT, there is this tantalizing possibility of making contact with experiments. So that's the end of my talk. Thank you.
Thank you for this very nice talk. Okay, first I would like to ask the audience here if there are any questions. Dita, please be patient.
Right, again, Dieter. Hi, Eran.
Hello, Dieter.
Thanks for this very nice talk. Really fascinating. My question is what you mentioned at the end of your talk. You have these various tests, and they're all, in all the CFTs you have tested, the spectrum is convex. But do you have any real understanding for that? Is it related to unitarity of CFT, or can you build counterexamples where you give up some of the, so to say, defining theorems of CFT? So I'm really interested to know whether you have a deeper understanding for this conjecture in terms of CFTs.
Yeah, so like I said, the general argument is just coming from the weak gravity conjecture, but from what I just showed, from pure CFT side, we don't know. I don't have a general argument for it. One can try to look at the data and see what could convexity be related to. So one thing that we've seen is that you can violate convexity in non-unitary theories. For example, the ON model in 5 dimensions is a CFT, which does not have convex spectrum, but it's also non-unitary. So that's why we insisted on unitary theory. So a natural statement could be that perhaps convexity is related to unitarity. But when we looked at this kind of Banks-Sachs model, you find that convexity is exactly mapped to stability of the vacuum. Okay, so if you took H tilde and F tilde to be negative, let's say, then you would violate convexity, but then you would also have runaway in the vacuum. And it's a one-to-one. So it's also true that the Owen model in 5 dimensions has an unstable vacuum. So perhaps the statement should be that convexity is related to stability of the vacuum of the theory rather than unitarity. Because, for example, the U1 model in 4 dimensions is actually non-unitary theory. It has some operators which are non-unitary. I didn't get to mention it, but it still has a convex spectrum, this theory. This has a non-unitary operators, but it still has convex spectrum. So it's not clear exactly what this convexity is related to. It seems to be satisfied in every unitary theory with a stable vacuum that we tested. But I think understanding from the CFT side what convexity corresponds to is an open question that we would like to understand. And if anybody has insights, that would be very interesting to know. This is all I can say. Sorry, I cannot answer anymore. I don't know the full relation, but
if there is any question from the online participants, please raise your hand. Not at the moment. So let's thank Eran again for this nice talk.
Okay, thank you. So I stop share the screen.
Thank you. And now we will move on with the next speaker, who is, I believe, Fotis Farakos.
Hi, everyone. Let me just share.
Hi, Fotis.
Let me share screen.
Okay. So Fotis is going to tell us about weak gravity, supergravity, and de Sitter Vacua. So Fotis, we can hear you. You may start.
Thanks. Thanks for the invitation, and thanks for doing the conference in this very nice and very successful hybrid form, so that some of us can also give a talk who cannot be there. So, okay, it moves. So let me start with the introduction and the plan of the talk. The central question that somehow underlines this talk is what if string theory has no de Sitter Vacua? And the reason why this is very interesting at these times is because it seems that the universe that we live in requires, we see this the expansion, and this means that the effective theory that would describe our universe should have a positive, if you want, a vacuum energy. This could be, in some case, a cosmological constant, but this is something that is, in some sense, under debate, because if you ask to have a cosmological constant, it means that on top of asking that your vacuum energy is positive, you are also asking that you have a critical point at a positive vacuum energy. And on top of that, that the mass matrix is a positive. The eigenvalues of the mass matrix of the various moduli you want to stabilize are positive. And also, one could also add that we are further requiring that if this vacuum is metastable, so if it has some sort of decay channel, then of course the decay should not happen immediately. So this is an extra assumption. Otherwise, of course, effectively it will be like a rolling scalar. And it has been, of course, it is extremely hard to find such constructions in string theory, almost impossible, in fact, especially in classical setups. And for this reason, this has been also deemed as a conjecture, telling you that, in fact, you cannot find the de Sitter Vacua with such properties in string theory. Now, I would like now to twist a bit the question and say, okay, maybe this happens in string theory, and we know that always supergravity, the supergravities we are interested in are derived and should be derived from string theory. But then how can we see this difficulty in a 4D effective supergravity theory, n equal 1 or 2 or more? How could we see this happening? Because the ingredients that we use in a supergravity theory are very few. You have a huge freedom in choosing the ingredients, but the ingredients themselves are few. So either you choose your superpotential in n equal 1, or in any supergravity, you choose the gauging that you're going to do. And finally, you can also study systems that have supersymmetry intrinsically non-linearly realized. And this again gives rise to a scalar potential, depending on how you use this nonlinear supersymmetry. But now you see the problem is that it's obvious that without a priori knowledge of the string theory origin of such ingredients, then, I mean, without exact knowledge, of course, we know that superpotential can come from fluxes, but if you don't tell me what exactly the flux is, I cannot restrict them in any way. So without a priori knowledge of the origin of these ingredients from string theory, it is in fact impossible to exclude de Sitter vacuum supergravity, because you can include any of these ingredients and it's very easy to get de Sitter in supergravity. So the idea that I would like sort of to discuss is what if we take the things we know about supergravity, but we only ask that we apply the restrictions on these ingredients that come from the swampland. Of course, you can tell me, okay, apply directly the de Sitter conjecture, then you have no de Sitter, fine. But what if we try to look at the restrictions from the swampland that directly can restrict the ingredients that we use to get de Sitter vacuum? Then maybe we can find that indeed there is something hidden in the structure of supergravity. For example, what are these restrictions that could restrict our ingredients? First of all, already we heard about the weak gravity conjecture. The version here that I will be interested in is the magnetic version that tells you if you have a gauging, no matter what happens, you are going to have a cutoff much lower than what you expected. So in supergravity, the cutoff is en Planck. However, this simple conjecture just tells you that your cutoff is not en Planck anymore. It's much lower than what you thought. And I will show you how this enters the restrictions on the vacuum structure. Of course, even the electric weak gravity conjecture still puts restrictions, but I will not need it here. Also, if you have ADS vacua that are not supersymmetric and are supported by fluxes, again, according to the swampland conjectures, these have to have always a decay channel. And finally, a third bound that I will show you the relevance of it at some point, a very interesting relevance, is the Festina Lente bound, which is more recent. And this, as you can see, puts bounds on the masses of fields when you are in a de Sitter space, and tells you that their masses have to be larger. The mass square is larger than their charge times the Hubble. And I will not go in more details about the meaning of the swampland and the conjectures, because you will hear a lot about them in other talks. So the plan from now on is the following. First, I will, as I told you, we can have gauging, superpotentials, and nonlinear supersymmetry. About superpotentials, I will not have time to say anything. I will focus on de Sitter vacua that can arise from gaugings and on de Sitter vacua that can arise from nonlinear supersymmetry. So let me start from the gaugings. So the simplest model that you can construct that gives you a de Sitter vacuum with the gauging is the one where you take a pure 4D n equal 1 supergravity, you couple to electromagnetism, And then you take the gravitino to be charged under the U1 of the electromagnetism. And this automatically, because of supersymmetry, also generates a positive vacuum energy. So in particular, this is the Lagrangian here. This is also known as the Friedmann model or the Fageli-Oculos term. It all boils down to the fact that you have a gauge, or you can even call it a gauge supergravity. Now, what is the important thing we should notice here in this extremely simple model? So we can identify the gauge coupling, G, small g, and we can identify the charge of the gravitino under the gauge vector. So psi is the gravitino. And then, according to the magnetic weak gravity conjecture, this would tell us that this theory here, even though you are in supergravity, so your cutoff would naively be M Planck, the cutoff, in fact, is parametrically smaller, and it is given by at least G times Xi times M Planck. So it is much smaller than you would naively think. But then you can also look at the vacuum energy of this theory, which is positive. So this is exactly a de Sitter vacuum. There are also no moduli here. And the Hubble of such the Hubble scale that corresponds to such a 4D de Sitter vacuum is exactly G times Xi times M Planck, which, according to the magnetic weak gravity conjecture, is exactly the cutoff. So you have here a situation where you are in 4D n=1 supergravity, you get a de Sitter vacuum, you say, fine, I mean, this thing is perfect, the smaller the G, the better, even the better. But in fact, we can already see that you are in trouble with the Swampland. And more or less, you should not expect that you are ever able to find such a thing from string theory, just because your Hubble hits the cutoff. And this is an observation that we did with Nicolò and George. And the thing that I would like to, for the moment, that is crucial for this setup is to explain a bit better now, is why when your Hubble scale is as big as the cutoff, why that can be problematic. There is, of course, for those who work on inflation, this is almost obvious that why such a thing is problematic, because the fluctuations of the scalar becomes very big. Or if you interpret the Hubble scale as an IR cutoff, again, you see the problem. However, I would like to give a more a simple EFT argument that you can find in our work with Nicolò and Gianguido, where we explain why such a thing is problematic. So when you are, and the reasoning is the following. Here, and when we find the Sitter vacuum in 4D supergravity, in principle, we are concentrating on the two derivative parts. So we have always standard two derivative supergravity. In order to be able to trust any result that we get from such a setup, we have to be confident that we can ignore all the higher order possible corrections. For example, you should be confident that you should ignore R square higher order supergravity terms. But you can already see that if, for example, we put a test R square term in the theory, then this in principle can have an order 1 coefficient, but should be suppressed with your cutoff. Now, on a de Sitter background, the Ricci scalar is proportional to Hubble square, and then automatically, immediately, you can notice that in order to be able to confidently ignore the higher order terms, we need the Hubble to be much more smaller than the UV cutoff, such that these terms are not important for the theory, and such that we can trust R2 derivative supergravity. Okay. So now let me go to, so this model, this example was about n=1. Let me go to n=2 de Sitter vacua. So you can take an n=2 supergravity, and it is known now how we can construct for them de Sitter vacua, stable, even stable de Sitter vacua in 4D n=2. This was done by Friedrich and Antoine in 2002. The first examples were out. So the ingredients you need are the following. First of all, you need 3 physical vector multiplets, which together with a graviphoton give you 4 vectors. And with those 4 vectors, you can gauge SO2, 1 times U1. The couplings of the SO2, the non-compact part, the SO2, 1, are I will call it E0. You can think of it as charge, but it's really the coupling. And E1 corresponds to the U1 factor. And just for completeness, let me mention that the scalar manifold, the special Keller manifold, is the SU 1, 1 over U1 to the third, because we have 3 plus 1 vectors. And there is no hypers here. On top of that, well, in this, if you just had these ingredients, again, you could not get a de Sitter vacuum. You have also to include symplectic rotation, which at that point was sort of something special called the de Roux-Wagemann's angle, which is a parameter theta. I'm mentioning here because we will see it entering the vacuum energy later. So this is just a rotation of your special of your symplectic sections. And finally, with the U1 factor, so with this U1 here, we will also gauge the R symmetry. And this means nothing but the fact that we are going to have the gravitini charge under this U1 as well. And the charge, of course, is going to be U1. These are the ingredients. Then you can minimize the scalar potential, and you find the de Sitter vacuum. Now, that de Sitter vacuum, the SO2, 1, of course, has to break, otherwise you would have ghosts, and it breaks to a U1. So the final gauge group that survives is U1 times U1. One of the U1s has a charge E0 related to it, and the other one has charges E1 related to it. And because both of them are massless U1s, you can apply the weak gravity conjecture to either one of them. And in particular here, we will apply again the magnetic version. Now, on the vacuum now, let's focus on the vacuum. You can notice, first of all, that the gravitino masses on the vacuum are 0. I will come back to this later. And also that the vacuum energy is positive, and it's given by the product of the two charges times sine theta. Now, for the moment, this looks that you cannot say much about it, especially because sine theta is just an angle, so it can have arbitrary values. However, the way you have to apply the magnetic weak gravity conjecture is you have to identify the gauge coupling, and I would say you are allowed always to multiply with the charge to get the cutoff, because in any case the charges are quantized and they are greater than 1. So in the worst case, you just have a stronger, a weaker bound on your cutoff. Now, if you and let me focus on the U1 that is gauged relevant with related to the Fageli-Opoulos term. So the one that has charge E1, and I can choose any particle that is charged, and here I will choose the gravitino to apply the magnetic weak gravity conjecture. So all I have to do is I take the gauge coupling for the U1 and I multiply it with the charge of the gravitino. Now the charge of the gravitino is E1. And you can identify the small g by looking at the kinetic terms of the vector, and they have the form that you can see here in the bottom of the slide. And then when you multiply them, you find exactly the square root of E0, E1 sine theta. And this tells you that your Hubble scale in such a de Sitter vacuum is exactly the same, or almost the same, is around the order of the cutoff. And again, as I already told you, this is catastrophic if you want to claim that you can trust the two-derivative theory, as we are doing here. And this is in the work we did with Nicola and Gianguido. So let me now highlight our results and further things that we did. So until here, I was talking about only n=2 vector multiplets. In fact, we have shown that even if you include hypermultiplets and you work in a 4D n=2 setup, all the known stable de Sitter vacua have exactly the same problem. And this is in a work we did later with Maxime and Matteo and Gianguido. And it seems, at least the thing that we see in all these cases is that there is always underlying them, there is the fact that the mass of the gravitino is 0, whereas the gravitino still remains charged under some U1. And in fact, this is directly relating now to the Festina lente bound, because the Festina lente would tell you, which was worked out by Miguel, Thomas, and Gerben already from 2019, the Festina lente bound would tell you that a theory with this assignment for the mass and the charge of an object is already the swampland. You don't have to search more. They would already know that this is problematic. Of course, here, this is a completely non-trivial cross-validation of the result. And in fact, for this reason, we had already deemed it as a conjecture that the Sitter vacua, so the Sitter stable critical points where the gravitino mass is vanishing, should belong to the swampland. And since then, there has been a lot of important developments, work by Nicolò, Dieter Lust, but also from other groups. And I will also not go into detail into that, because for sure Nicolò will talk about it. And now, since I'm finished with the part relating to the gauging, I will go into the part relating to the de Sitter vacua that can come from nonlinear supersymmetry. Please tell me if I am too slow or if I'm all right with time. Okay, so let me go to the restrictions on Vacua from nonlinear supersymmetry. So the simplest model that I will discuss is you should think now about the situation where the KKLT construction, the most simple realization, let's say, is adapted to for the n equal 1 supergravity. The construction is the following. First of all, you start with a no-scale Keller potential and the superpotential that includes also the constant term and the non-perturbative correction. So that would correspond to the blue line. Then you include the nilpotent chiral Goldstino, and this captures the effect of the anti-T3 brane that uplifts your vacuum energy. And the way to include the nilpotent Goldstino, this uplift, is that you add just a flat term for the Goldstino and the linear term in the superpotential, and that is enough, as has been shown by Ferrara, Carlos, and Lite in 2014. And then if f is small, you are in non-supersymmetric ADS vacua, but of course, if you tune f carefully, in the end you get a very shallow de Sitter with a very small cosmological constant. The important thing again to notice here is that since f is a constant in 4 dimensions, especially in the particular setup, there is no way that you can tell the difference between the small f and the star f4. So, or if you want, a star DC3. So in some sense, you can always interpret this small f as a flux, as a C3, so as a flux of the C3, so as an F4. But then, according to the swampland conjecture, it means that such an object has to have a way to decay. Because, for example, you could be in the situation where you are in the purple line, where you are in non-supersymmetric ADS, and this always has to have a way to decay. So what I will show you now is that we can include a decay channel for the Goldstino in 4 dimensions. And of course, I will not focus in the ADS decay in the ADS to ADS decay. I will directly include the decay channel and focus on the decay from the minimum of the golden line to the minimum of the blue line. So from the realistic de Sitter to the supersymmetric ADS. So the way to include the nilpotent Goldstino is that you take a standard chiral superfield. You take a chiral superfield. What's this? 10 minutes, all right. So you take a chiral superfield and you So in the lowest component, you have a complex scalar. In the theta component, there is a fermion, and the theta square component is the auxiliary field F. And of course, the F is the guy who gets the VEV and lets you know that supersymmetry is broken. On top of that, Nilpotent-Goldstein's chiral superfield means that you impose the condition that x squared is equal to 0. And in principle, if you are in a background where supersymmetry is broken, this always eliminates the complex scalar A. However, I would like to take a more closer look into this equation. So this is a quadratic equation for the chiral superfield X. Now, because it is quadratic, in fact, it has two solutions. One solution is, first of all, if you are assuming that you are in a background where F is non-zero, then of course you have to solve it by eliminating the complex scalar A and turning it into G squared over 2F. And then you are going to find the Volkov-Akulov theory in your background. And this is exactly the contribution that leaves your vacuum energy to the sitter. However, you can still impose the condition x squared is 0, even if supersymmetry is not broken. But in that case, there is only one solution, and that solution is to have x to be 0. There is no other solution that is consistent with the supersymmetry transformations. So if you put any other solutions, you're gonna break supersymmetry explicitly. But then you see that when x is 0, then it means that there are also no fluctuations, because also delta x becomes 0. So in fact, when you are in the second case, the Goldstein becomes, in some sense, evaporates. So the uplifting contribution completely disappears, but also all the sector related to that disappears. And this is, of course, something that you might know from string theory as I don't know if this is exactly the same procedure, but it's similar to the so-called KPV. Now we'll skip a lot of the technical details and just tell you exactly fast the basic steps. So the way to see the decay, as I told you, we want to have a decay channel between the very shallow de Sitter and the SUSY ADS, which means we want to have a way to tunnel between the case where we have F non-zero and there is a Volkov-Akulov, a full Volkov-Akulov model, to tunnel to the case where the chiral superfield vanishes completely. And there is a way to do it because we can exchange the auxiliary field of the chiral superfield to a 3-form, and then the 3-form can couple to a membrane. In fact, according to the Swampland, it should couple to a membrane such that you have a way to decay. So you could have a region, a spherical membrane or a spherical domain wall, where outside you have the Volkov-Akulov model and the de Sitter, and inside the Volkov-Akulov completely disappears, and you have your SUSY ADS. Then we have to identify the charge and the tension of the membrane. The charge, of course, in order to do the jump in one go, you have to identify it with the supersymmetry breaking order parameter. And we should also identify the tension of the membrane. Now, for the tension, I do not know of a specific way to give it a value. However, for the moment, it is reasonable to assume that the tension is up to the UV cutoff to the third. And this happens because otherwise the object becomes too heavy and it decouples. So with these assumptions, right, which I stressed, especially the property of the tension is an assumption, you can calculate the decay time from the de Sitter to ADS according to the Brown-Teitel-Boehm formula, and you find that in fact the de Sitter is very short-lived. So once again, this is interesting because it tells you that if such a procedure is existing in string theory, then indeed the KKLT will decay very fast. But of course, I think the crucial thing here is to understand exactly what could enforce the tension to be cut off to the third and not bigger. Because obviously, if you make the tension grow, then the object becomes heavier, and of course the decay becomes much slower, and this means that the state vacuum will become long-lived at some point if the membrane is heavy enough. So let me conclude. Let me go back to the starting question: what if string theory has no Dester vacua? And what I try to argue is that it might be possible. An optimistic point of view is that we might be possible to see this problem in supergravity if we equip it with the Swampland conjectures that put conditions on the ingredients that we are using, so the masses, the charges, and so on. And as I already showed you, we can get, in cases where you have uplifts from SUSY ADS to non-supersymmetric de Sitter with a nonlinear realizations, then you might be forced to have a very short lifetime for such vacua. If you have a de Sitter vacua that comes from gaugings, you might be hitting various cutoffs that pure supergravity cannot see. And finally, you can break supersymmetry with superpotentials and get a de Sitter vacua. But for the moment, I don't have direct some direct argument of how to constrain the superpotential, but there has been work relating to how superpotentials arise from three forms by Lanza, Marchesano, Martucci, and Irene. And in this way, they also get restrictions on the de Sitter vacua in some cases. So with this, let me thank you also.
Okay, thank you, Palti, for this very interesting talk. Okay, first I would like to ask the audience in the auditorium whether there is some question. I don't see anything at the moment. Maybe we ask the online audience whether they have a question. They can raise their hand. There is something, okay. Carlo?
Yes, thank you. Thanks a lot, Fotis, for the nice talk.
Hi, Carlo. Thanks.
I have a question about the very first example that you discussed with the Fayet-Leopoulos term.
Yes.
What about the new Fayet-Leopoulos terms where the gravitino is not charged under the U1?
Yes, that's in fact something very relevant. So in that case, you have no restriction because the gravitino is not charged, and also you can add a mass for the gravitino. So you completely sort of evade this problem. But there, if I may add, you have supersymmetry is somehow intrinsically always broken. So
yes.
It might be restricted for some reason from the restrictions you need to put on nonlinear realizations, but that is something that is not clear to me now.
Okay, thanks.
Hello.
Luca, hi.
Hey.
Yeah.
Hello. Hi, Fotis. So thanks a lot for the nice talk.
Thanks.
So I have a question about your latest example, the one on
the nonlinear or the n equal to?
The nonlinear realization with four-form fluxes.
Yes.
So just to understand, when you at which point are you invoking any swampland condition?
The fact that in principle I could have the uplift comes from this contribution to the superpotential. Now this f is a constant, but in 4 dimensions you know that I can trade it with an f4, right? Now,
okay.
Because I can always you can always trade it with an f4, with a SAR f4.
Yes, but maybe f4 needs to be appropriately quantized if it's related to some compact gauge symmetry, right?
Of course,
so are you assuming
yes.
Any
quantization
relaxation of this quantization?
No,
okay.
no.
Anyway,
the quantization doesn't enter. But then you see if you can always have an ADS vacuum that is not supersymmetric, and then automatically you have to have a decay channel for such a vacuum for the purple line. This means you have to put the membrane in your theory so that the system can decay.
Okay, but sorry, the nonlinearization was used to get the sitter. So I see.
Oh, at any point where you go above the blue line, you need the nonlinearization. Of course, you can put it to be at the sitter, but I mean, it's the same tool. You cannot say, now in the sitter, I don't know, and suddenly if I go a bit below, you know, there is a decay channel. If the decay channel is there, it's there. It should not be related to exactly your background, I would say.
Okay, thanks.
Is there another question? I don't see any. Okay, let's thank Fotis again. Thank you, Fotis.
Thanks. So I stop.
And now we can move on to the next talk, which is by Julian Zona.
I can share my screen. So
I see now who has already shared his screen, and the title is Ergodicity in Quantum Gravity. Julian, you may start.
Okay, so I will take about 30 minutes if I understand correctly. So first of all, many thanks for putting on this conference and for inviting me to speak here. And also thanks for those who've made possible this slight change of the schedule, which I apologize for. So this talk today is based on quite a lot of recent work that we've been doing with this wonderful set of collaborators. Maybe in particular, I would like to highlight my postdoc Pranjal Nayak in Geneva, who's done really a lot of amazing work here and who is just a very, very good postdoc who's going to be on the job market this fall. So let me start by giving you an introduction. So the goal is actually not to maybe bombard you with all sorts of results, but to actually give you more an idea of where we're coming from, why we're doing these things, and what's behind. And then I do have a selection of examples, but I'm not particularly attached to have to cover them all, though, so we'll see where we get. So the general context is quantum gravity, but there's a strong showing of quantum chaos. So both of these I would like to tell you what they are and how they are related. So of course, most of you, or probably all of you, know that quantum mechanical unitarity and gravitational physics haven't been getting on particularly well. Two examples that I will come back to in this talk. One is the black hole information problem that was, of course, brought to us by Stephen Hawking, but that is maybe most sharply formulated in terms of the famous Page curve. So this has to do with the unitary or otherwise evaporation of a black hole. But then also maybe slightly more down to earth problem that is just related to the long time behavior of observables, where again, if you look at even such simple observables as 2-point functions as a function of time, you can actually find, well, evidence of this fraught relationship between the expectations of quantum mechanical unitarity and the actual predictions of semi-classical gravity. All of these paradoxes, in particular the two that I just mentioned, arise because we like to attempt to interpret black holes themselves as thermodynamic entities, which of course goes back to the groundbreaking work of Bekenstein and Hawking. So if black holes are thermodynamic entities in the precise sense that the black holes are in some sense thermodynamic ensembles, then it is, of course, an important question to understand how do these states ever arise? And this strategy, namely to study the problem of thermalization, the approach of these thermodynamic ensembles at all relevant timescales has proven to be very fruitful, in particular in the context of ADS-CFT. So if we think about gravity in this context of ADS-CFT duality, then we can make actually these ideas very precise. We can precisely, using work of Gibbons and Hawking, associate a thermodynamic ensemble to the black hole in the bulk. And we can also precisely ask the question, what happens if I set up my holographic system, either from the field theory point of view or from the bulk point of view, in a non-equilibrium initial state? How and when and exactly in what precise way does it approach the thermal state? So this is just a visualization. ADS here, let's say ADS3 is this hot tin can. And I set it up in some initial state, and that initial state is supposed to have the effect of eventually forming a horizon and an attendant singularity of the black hole in the bulk. And actually, to understand this process of thermalization in a unitary theory and how this is compatible with the bulk physics we observe is precisely the strategy that we're following, and is also the reason why quantum chaos and the idea of quantum ergodicity is going to be particularly insightful. So, right. Then using these ideas that, okay, let's see of how these thermal states can ever be essentially attained by generic thermalization dynamics, has actually led to great progress recently. And in particular, on these questions that I just mentioned, namely the page curve itself and also the behavior of correlation functions. But as often is the case with great leaps forward, once the dust settles, one realizes that they have actually produced other puzzles that are perhaps equally intriguing. And one of the most intriguing and important ones that has come out of this recent progress is that gravity in ADS at least seems to contain contributions, namely so-called Euclidean wormholes, which strongly suggest that what is actually at work is not a single quantum system, but an average of an ensemble of quantum systems. Now, this connection between wormholes and averages, I'm more than happy to talk a little bit more about, but here I'm just trying to give you the initial flavor. So to my mind, the point is now that we can actually have two attitudes to this, this seeming problem between what gravity says, namely there are wormholes, and the fact that in order to understand that in a quantum system way, we need to introduce ensembles. Well, we can say that firstly, we could just say, well, that's just how it is. The ensemble is actually a fundamental ingredient of how we should understand gravity. So in other words, one bulk theory is in fact dually described by an ensemble of quantum systems on the boundary. The second point of view that we can have is that this ensemble actually is itself not fundamental. I'm using the word emergent here, but I want to be more precise about what I mean with this emergent as the talk goes on. So in other words, there is still fundamentally only one bulk theory and only one boundary theory, but this ensemble description actually arises, and it arises precisely because of the dynamics of quantum chaotic systems. So this idea that the ensemble is emergent is one that comes from the theory of condensed matter, and it has been already well described in the context of disorder models, but in particular also in the context of quantum chaos, which is the one that's relevant to the story that I want to tell you. Now, because I've already spent more time on point 2, you can probably guess that I'm going to come down on the attitude number 2. But I also, of course, have to acknowledge that 1 is certainly not ruled out by what we know so far. Okay, but I hope that it's clear, you understand. Either we really have to accept the fact that if we want to get a unitary page curve, or if we want to have the right long-term dynamics of 2-point functions in the way that recently has been produced, we have to deal with this issue of the ensemble. And either we accept that it's a new way to think about ADS-CFT, and then maybe even broader about gravity, or we try to embed it in the way that we used to understand ADS-CFT, namely one boundary and one bulk. And this is what I'm trying to do with this work and in this talk. So, somehow this quote came to my mind. So, you know, the three musketeers, one for all and all for one, because of this idea that one theory can look like the ensemble, and then of course, vice versa, the ensemble can look like one. And in writing this, I actually noticed that it was unofficially the motto of the Swiss Confederation in Latin. So one for all and all for one. It has recently been pointed out to me that in fact, this goes back to Shakespeare and, of course, not the Swiss Confederation, but there are different theories about that too. So, a French person might say it's Dumas, German person say it's Goethe, British person says it's Shakespeare. But at any rate, this is really the motto. One system can behave like many, like the ensemble, and the ensemble can look like one system. And I want to tell you how this works. So the way that I'm going to establish this is I'm actually going to try and base all of the phenomenology that is related to these wormholes on an effective field theory. So an effective field theory that basically gives rise to the kind of correlations that are encoded in wormholes. And in order to construct this effective field theory, I need to, or the most powerful way of doing so is to identify a symmetry principle and a symmetry breaking principle, which basically constrains what the effective field theory looks like. And the relevant symmetry is one that we call causal symmetry. And why should become clear in a few slides. So what's really nice about this is that conceptually, this thinking about it this way explains, as I've been advertising, the role of the ensemble for individual theories. And it also explains why one might expect to find wormholes in the gravity duals of individual theories. But it is at the same time also quite an effective technical tool, as it is often the case with effective field theories. So it allows us to make specific quantitative predictions and in particular applications to the role of random matrices in black hole physics, the role of the eigenstate thermalization hypothesis in ADS-CFT, and also this recent OPE randomness conjecture, which I also want to say a few words. Now, at this point in my talk, maybe I can ask, would you like to hear a little bit more about why these wormholes seem to suggest an ensemble, or is this something with which the audience is sufficiently familiar that I should go into the more meaty part of my talk?
Yeah, maybe it's a little bit to assess that at the moment. It's difficult to assess that at the moment. So maybe you choose what you would like to do.
Okay. Well, then I'll go on with my talk. And if there are things that are very unclear, I have a bunch of backup slides to try and make the statement that I just made, that these wormhole contributions seem to imply an ensemble. So let me give you a little bit of background on quantum chaos and then immediately launch into how this has to do with these gravity observables. So quantum chaos, we've heard many talks about quantum chaos in recent years. But most of them, at least in our community, were actually about what I would call early time chaos. So this is this stuff about Lyapunov exponent, maximal chaos, and so on. So what I'm going to talk about is a different notion of quantum chaos, maybe the one that people came up with first. So this is how the quantum chaos community really thinks about the manifestation of chaos in quantum system. But I just want to say that this is a different point of view as the one related to Lyapunov exponent. And in particular, what we talk about here is not necessarily so much dynamical things and trajectories, but we talk about the spectrum of quantum systems, which of course is the most fundamental aspect of a quantum system. So this goes back all the way to Wigner in the 1950s. And said in modern parlance, let us take one quantum system, one Hamiltonian, and let us take one which is chaotic. So a simple example are these billiards in, like non-integrable billiard tables. So if we look at the energy levels of this one quantum system, we diagonalize the Hamiltonian, we can ask the following question. Let us fix one energy level. I pick one, let's say the 7th excited state. And then I scan through the spectrum and I ask, how likely is it that I find another state, another energy eigenstate? And how do I do that? Well, I draw a histogram, which I've shown here in gray. I draw a histogram of actually the number of energy levels that fit into a given bin. I need to choose some bin size for this histogram. And the statement is that if I take a limit in which this histogram becomes infinitely fine-grained, then this actually converges onto a limiting distribution, which is this purple curve, which is the one that has been predicted by Wigner. And interestingly, the form of this curve here, so S, by the way, is just a measure of energy in certain units, in units of the mean spacing between levels. So, so this is the basically frequentist probability of finding another level if I have fixed myself to be in one given energy level. And this continuous function here, known as Wigner's surmise, well, it was guessed by Wigner, and what he guessed was basically that this is the energy distribution that you would get if you were in one of the random matrix ensembles that are now known as the classical ensembles. So you sample the Hamiltonian from a random distribution, for example, the Gaussian orthogonal ensemble. So this is really everything here in a nutshell. Okay, there's a lot in there, but the point is that we look at the single quantum system and we say that its level spacing statistics is actually approximated in some sense arbitrarily well by that of an ensemble. Okay, so this is the connection between one system and an ensemble. But this makes an appearance, of course, in many other quantities, and the one that is most used in our community is very related. It's what's known as the spectral form factor. And the spectral form factor is, in a technical sense, essentially the Fourier transform of this. So this is a curve that is a function of energy differences. And so I can, of course, Fourier transform into real space. And then I have a time, which is dual to energy differences. And the quantity that gives the time dependence of this Fourier transform is what's known as the spectral form factor. And why is it known as the spectral form factor? Well, because you see, the larger the time gets, the smaller in energy space I probe. So the smaller gaps in eigenvalues I probe. So that the more that the time goes on, the more fine-grained this observable probes the energy spectrum. And the fact that this energy spectrum approaches some universal distribution is precisely manifested in this ramp and plateau part of the spectral form factor, which you've probably heard about. So the spectral form factor of some black hole is supposed to have some initial decay, but then it starts rising linearly. This is known as the ramp, until it saturates on what is called the plateau. And this linear rise with the right coefficient and the plateau with the right coefficient are precisely predicted by this Wigner. Okay, and so there are two important time scales. The first one is called the tauless time. This is when the system, also known as the ergodic time, first starts showing this random matrix behavior. And then this thing here is called the Heisenberg time, which is when the plateau starts. And again, so the point is that the spectral form factor for an individual system will look like this, which at late enough times looks exactly like the one you would have predicted from an ensemble. And so now what I need to tell you is how is this manifested in gravity and what does it have to do with wormholes? So there I want to give you already the one slide overview of what's going to happen. Well, everything here in this blue region is described by what we used to know just as semi-classical gravity. So this decay here can be calculated in area CFT simply by all the rules that you have known. For example, you calculate the partition function at some inverse temperature, you analytically continue it, you get exactly this decay. In order to get the ramp, this is the first time that we need to have a new ingredient, and the new ingredient is basically that, yes, you still do semi-classical gravity, but in semi-classical gravity, there are also solutions which have multiple asymptotic regions, and these are known as Euclidean wormholes. The Fourier transform of the gravity contribution of the semi-classical wormholes gives precisely the linear ramp with precisely the right coefficient. And well, at very late times, this plateau is a little bit more complicated. I can't just show that in a nutshell, but this has to do with the restoration of causal symmetry, and I'll hopefully get there by the end of my talk. Note, by the way, this is a log-log plot. So when I talk about tauless time, this is already very, very late time physics. And if we're talking about these quantum chaos notions like Lyapunov exponent and so on, they would be much, much earlier. They would be hidden somewhere here in this blue region. So this purple region and the dark purple region are really the new regions that we're probing. This is when these systems show ergodic behavior, and this ergodic behavior is precisely encoded by what we call Euclidean wormholes in the bulk. All right, so let me just tell you a little bit about a little bit more technically about what's going on. So what is this causal symmetry and why is it interesting? So the main idea of causal symmetry breaking is that, well, we want to know about the spectrum. We want to know about the spectral density. In particular, we want it to have correlations of eigenvalues. So we need to have at least one copy of the spectral density, rho of E. Well, we all remember from our many-body course or from our quantum field theory courses that the spectral density can be seen as the discontinuity of the correlation function across a cut. So this is the advanced correlation function. This is the retarded correlation function. And if there is a non-zero of discontinuity, then the spectral density is also non-zero. So fine. Now, this is what I'm saying here. The key idea is now that within this formalism that I'm laying out here, we can understand the fact that the G plus and the G minus correlation function do not give the same answer, because you see, if they did give the same answer, then the spectral density would be vanishing here. We can understand this fact as a spontaneous symmetry breaking, namely that there is some theory, which I will develop now, whose mean field gives you a different value for G plus than it gives you for G minus, in such a way that G plus minus G minus precisely reproduces the spectral density of the original theory that you were interested in. Now, why do I have these bars here? Well, that's because in order to stabilize this effective field theory, I need to do something. What I can do is I can basically average. So I can do something like we do in SYK, but then you might say rightly, well, but you just told us that you don't need to do averaging to get this phenomenology. Well, then I would say we actually do what the chaos people do. Namely, we just think of the eigenstate, the distribution of eigenstates as a statistical quantity, and we analyze it statistically. And all that is saying is we do this histogram, and then we take a limit of the number of bins going to infinity. But that is intrinsically a little bit of energy uncertainty that you have at each step. And that's why it allows you to stabilize this effective field theory as well. But we never have to actually invoke that there's more than one quantum system, okay? So we just think of the energies, the spectrum, as being some sort of system that we analyze statistically. We want to understand now the statistical properties of the energy spectrum of one system. So then how do we do it? Well, in order to understand then the statistical distribution of two copies of rho, I basically have to write a generating functional that allows me to study the statistics of any number of copies of rho of E. And the simplest example, the one that allows me to study two copies, is the one that I'm writing here. It's basically a ratio of spectral determinants. These are very much related to spectral resolvents, but it's important that I use spectral determinants. So the Z's will be like energies. H is the Hamiltonian of my quantum system. So think, for example, n equals to 4 super Yang-Mills. And I'm having two determinants here and two determinants in the denominator. The fact that I have two determinants in the denominator is simply that I will take derivatives of this quantity with respect to energies, and then I want to normalize, and the normalization is basically the fact that I have one over determinants. So in particular, taking two energy derivatives of this quantity and then setting the energies equal to each other in pairs produces precisely a correlation function, rho times rho. This is what we want, rho times rho correlations, because that was what gave me P of S. Now there's a very simple trick. I can actually exponentiate this by writing these things as Gaussian integrals, two bosonic ones and two fermionic ones. Bosonic ones for the denominators, fermionic ones for the numerators. Then the theory here has actually what is called the causal symmetry, because the Hamiltonian is actually the same. This psi is a vector which is 4 times the size of the Hilbert space, right? Because each of these matrices is a matrix that has the size of the Hilbert space. So I have 4 times the size of the Hilbert space. But I have 4 times the same Hamiltonian, because this Hamiltonian here is the one of the same quantum system. So there is actually a rotational symmetry, which is a graded symmetry, which rotates each of these copies of the Hamiltonian into each of the other copies. And it's precisely that what we call causal symmetry. It is broken if rho is non-zero, precisely according to this breaking scheme here. U2/2 becomes a U1/1 times U1/1. So this is basically what these saddle points do. All right, so then the fact is that what we need to do is, well, we need to basically identify the goldstones of the symmetry breaking, which was taught to us by Callan, Coleman, Vest, and Zumino in the 60s. It's really just like they did in this high energy context. And what they told us is that we just look at the symmetry breaking pattern and we write a nonlinear sigma model on the coset of the full symmetry times the unbroken, quotiented by the unbroken symmetry. And so we write, just like Callan, Coleman, Vest, and Zumino, we write this super coset sigma model on this super coset. And what I want to just say 2 words of one, there is actually an analogy between what happens in QCD. In QCD, you have chiral symmetry, which is broken by a chiral condensate. Here, we have what we call a causal condensate. So this is like spontaneous expectation values of these auxiliary variables that are used to exponentiate these determinants. But they take on some physical meaning as, if you want, these things are like the mesons of our theory. And then, of course, the chiral symmetry is also explicitly broken by the quark mass. And our causal symmetry is also, in fact, explicitly broken. And the breaking scale is precisely the energy difference that we're interested in between 2 energy eigenvalues. And what I want to point out is that the energy difference between 2 energy eigenvalues is approximately of the size 1 divided by the total number of energy eigenvalues. So it's e to the minus the entropy. And it's really this is really a key of why what we do is so powerful, because it is intrinsically something that's very non-perturbative, and it would be very difficult to describe physics at the energy level spacing that is this fine-grained, but it's very natural here because these Goldstone theories work better the smaller the explicit breaking scale is, if you want. So this allows us to write down basically now an effective field theory that has a perturbative expansion, which from the gravity perspective is something that's highly non-perturbative. It's e to the minus s is the expansion parameter.
About 4 minutes.
About 5 minutes, you say?
4.
Okay. So then when we do this, what is wonderful is that this perturbative expansion arranges itself into a topological theory of gravity. So this is something that I showed with Alex Altland, who is an expert on quantum chaos, world expert on quantum chaos. And so I've just sort of shown this here schematically. So we have like something that we will identify with the wormhole, something that we identify with the wormhole with additional non-trivial topology and so on. Plus, there is also a second saddle point. I don't know if I have enough time to really talk much about the second saddle point, but there is basically a similar expansion with non-trivial bulk topologies and non-trivial expansion. And the nice thing is that we can, of course, use this to compute all these coefficients. So these are just the diagrams that I'm drawing, but we compute the coefficients quantitatively, and we can compute them with which has been computed, for example, using JT and this approach of the Stanford group. And in fact, we agree, and this chaotic effective field theory gives the same coefficients in this expansion. So then let me actually just give you an overview of what can be done. Well, I have just kind of shown you how it explains spectral correlations, namely the ramp plateau. And I want to say that the ramp plateau structure that is found in an individual theory, so provocatively, for example, n equals to 4 super Yang mills, is a consequence of universal ergodic dynamics. And the bulk manifestation is precisely the existence of these 2 boundary wormholes. Okay. Now, I will certainly not comment on SYK because I didn't have the time to make any of those comments, but I want to say one more thing. I want to say that we have now thought about statistics of eigenvalues, but one can also think about statistics of eigenfunctions. And once one thinks about statistics of wave functions, you can start to talk about operator correlations, and you can actually derive something like the eigenstate thermalization hypothesis using this. And you can derive something like the recent proposal of a statistical distribution of OPE coefficients in CFTs, which is actually a proposal by Belin and Deboer. And well, in forthcoming work, we actually show how this fits in our general framework. And there was some previous work in which we pointed out how that might work. So let me just say this thing about wave function statistics then, basically. So as I said, you can think now about matrix elements of operators because they are, after all, just given by these expectation values with respect to the wave functions that you have in your system. And if the wave functions have some statistical distribution, they induce a statistical distribution on the operators. Technically, we do this by introducing something we call the operator resolvent, which is sort of like the previous resolvent, but we dress it up with the operator like so. And this can also be done using our EFT. It just is a slight technical complication. But what we find is we actually find, again, universal behavior. So I'm giving you here something which we call the operator sign kernel. This is a universal contribution to the late time behavior of these correlation functions. But I think it will be simpler if I just tell you what that means in real space. It means that even operator correlation functions have this sort of behavior that they initially decay. This is our semi-classical behavior. And then they have ramp and plateau, as is required by the requirements of unitarization. So this is like the proper unitary behavior of these two-point functions. And we can actually associate the proper unitary behavior with this ergodic behavior that I made a point about. We can also find some way of using this to show that these operators satisfy ETH. And this is nice because it basically invites a comparison to what we do to work of the UBC group, which actually pointed out that in order to interpret wormholes in the bulk, you might want to think about ETH, and we have a precise manifestation of how that works. Now, OPE correlations, well, let me just say that you can write OPE coefficients in conformal field theories like so. So they're also basically operator matrix elements. So it's maybe not so surprising that we can make similar statements about statistical behavior of these CIJKs. And this behavior is precisely the one that had been conjectured to be true by Belin and Deboer not so long ago. So let me go to my conclusion because I don't want to take too much of your time. So this causal symmetry breaking gives you a way of thinking about quantum chaos, ergodicity, as an effective field theory. I think it is nice because it gives you a way to think about ensembles in single theories. And I gave you some overview of what you might calculate with it, but you can of course calculate much more with it. It's fully non-perturbative, as I pointed out. It boils down to some very simple geometric principle, namely this coset, superspace coset sigma model. Okay, I showed you some applications, but more interesting open questions and directions. To me, the most interesting is what really is a geometric bulk way of thinking about causal symmetry. So we have some level of understanding in minimal string theory. So if you want to know about that, this is in this paper. And in JT gravity, which is essentially just a reinterpretation of previous work by the Stanford group. But if you want, the real question is, how do we do this in higher dimensions? Okay, and so to put this into a precise question, which I think will lead directly to the answer of how to do this in high dimensions, is how do we understand these saddle points that I showed in high dimensional bulk spacetimes? Is this related to these constrained instantons? Is this related to, you know, simply the Maldassena-Maus, or do we need to think about a completely new way of thinking about it? Particularly, can we classify what is this Andreev-Altshuler saddle point? So sorry for going slightly over time. Thank you very much for your attention.
Okay, thank you, Julian, for this very interesting talk. I invite questions from the audience in the auditorium. or maybe from online participants? I don't see any questions yet. It was a very interesting talk, nevertheless. So I would like to thank Julian again.
Thank you.
And at this moment, I think we can have our coffee break. Since we ran a little bit late, maybe we reconvene at 6:10 local time, obviously. So about 25 minutes. And
enjoy your coffee and see you. Bye-bye.